Right, everybody here. Yes, thank you for having me. I'm going to be talking about major cloud production challenges. And as you can see, this was a presentation I gave at IBC with John Mayotte from Imagine Communications. He's not here, obviously, so this will be a two-part presentation at the time. So this was, I talked about the sort of why we have these problems, what we're trying to solve, and John will talk about the how. You'll kind of see John's section is a lot more technical than mine. I'll try to do it slowly, and I'll try to also give some time for questions because some of the diagrams might take a bit of explanation. Likewise, on the other hand, heckles are also welcome. I think I forgot who I was talking to about seeing Jimmy Carr handle a heckler. I'm more than happy to see if I can emulate him. Code of conduct. Yeah, true. I think true. So yes, let's get going. Here's my classic intro slide. Usually this slide is for the Americans, but so what do we do as a company? Open Broadcast Systems. We specialize in software-based encoders and decoders for sports, news, and linear channel contribution at B2B, based in central London. So usually for the last 2 years, I've been sitting at my desk pointing to the left and saying Big Ben's over there, and Americans have been enthralled by that. So please pretend Big Ben, well, it's more over that way, but well, actually I'm not sure where I'm geographically in this room, but anyway, pretend that it's enthralling to you. We build everything in-house, high-speed electronics, high-speed networking, software, every single line of code, C and assembly for people who are interested. Every single thing, you name it, we do it. Not to be confused with the other OBS. This is regularly confused with the other open broadcast software. Not the same thing, right. What is Ground, Cloud, Ground? So today I'll be talking about the work of the Video Services Forum, which is kind of a working group to standardize technically some of these technologies, but I speak in my own capacity, and I think John also speaks in his own capacity. If you have any better ways to explain ground, cloud, any better terminology, I think everyone would love you to have a better word for this. But, oh, my images don't show up. Anyway, never mind. The pandemic showed us the cloud can basically take over our lives. There were compute-heavy services that scaled on demand, Zoom, cloud-hosted email, social media, Amazon, Netflix. But one notable area where this wasn't the case was television production. This is pretty much all on-prem. All mid to high-end production is some form of on-premise production. But cloud economics is really useful for broadcast, in particular for sports, mainly happen on a weekend. But we still have to have the peak amount of equipment in a facility. But we're paying for this equipment, and we're paying for electricity, this, that, and the other, that's staying idle most of the time. So what's technically stopping us from doing complex mid to high-end productions in the cloud? And this is basically the sort of my section of the presentation. Ah, this picture's come up now. Interesting. But I've been doing live cloud production. Well, yes, some people have, and some people haven't. Most of what's been going on has been single-based sort of, is that me getting a call? Somebody else getting a call? Anyway, single-based monolithic applications, sort of channel in the box, production switches, playout servers. These use the cloud as a home, but they're not necessarily a scalable architecture around it. Often, either these are single-vendor monolithic applications, they do one of everything, or they have some kind of proprietary transport. Probably the most well-known is NDI. But to get widespread adoption, we must have multi-vendor interoperation, appropriate picture quality levels, and we'll talk about that, standards for ground, cloud, ground, and some kind of agreed mechanism for building a workflow. And this is a sort of classic technology chart where the early adopters and innovators pick some kind of, I'd say, less open. But we want to reach a stage where we can do multi-vendor cloud production and have, as I'll show in a minute, uncompressed and have latencies comparable, not necessarily the same, but comparable to what we have on the ground. So not 30 seconds or 1 minute delayed, but something comparable. What makes it difficult? And really, what really makes it difficult from a traditional broadcast workflow is the ground. We have these existing workflows that in many cases we've had for decades. They have SDI, ST2110, satellite, cable, over the air, or Freeview, DVB, DTT. In particular, these workflows have very, very well-defined linear timing models. SDI in particular, 2110-21, and the VBV and MPEG-TS, very well understood linear timing models. And really in production, we want to have a timing model that means we don't have some kind of variable or undefined latency. And this is kind of one of the reasons, not the only reason, but why my web stream's 20 or 30 seconds behind that of broadcast. Because on the web, you don't really have a timing model. The timing model is guess a number and hope it's big enough. So yeah, what are my neighbors cheering about? We also don't, when we're cutting between feeds, we want a fixed latency between these feeds. We don't want to see a goal again happen from a different camera angle or a car overtake another car again, because these two feeds have a different latency. So if we're doing cloud production, we need a way of having a defined timing model. I'll do 2110 in the cloud. I don't have the time to go and explain the intricacies of 2110, but there are some people claiming to have 2110 in a public cloud. As of now, it's not possible to do in any public cloud. In particular, the precision time protocol that's used doesn't exist in any sort of public cloud. Each cloud handles time in their own different way. I can go into really the intricacies of that later, maybe. Cloud networks are shared. You share them between other people, and they have packet loss. 2110 kind of has a model where it's implied you have no packet loss, or you have a mechanism such as sending over two different networks to compensate for that. And in a practical implementation, you don't necessarily have access to the network card capabilities to do 2110, in particular packet pacing modes. But is this even a good idea, is a big question. Because the whole point of, do we really want to replicate what we have on the ground, or we have a linear lockstep chain? And the answer is no, we don't want to do this. We don't want linearized processing in the cloud. We want to be able to have the cloud instances run faster or slower than they need to be, just as long as we know the worst case and can accumulate the worst case, so that at the end, we know the accumulated worst case value. We also have another technical challenge, which is how do we handle synthetic sources in the cloud? So there are clips, like replays or something, you might be playing out from the cloud. Well, the cloud has a different time source to that on the ground. It might be close, but it's not necessarily the same. And cloud vendor-specific transport is a pretty hot topic. So to get the benefits of the cloud, we must trust the cloud. And cloud providers have their own internal bulk transport protocols of various forms. And what we really need is some kind of throughput, but with reliability. So we can push large amounts of data. All this data arrives in one piece in the way we want it, but also we have a latency. So all my data arrives on time. So in Europe, for example, generally we make television at 25 frames a second. So that's 40 milliseconds a frame. Well, it's not good enough if that frame arrives 45 milliseconds later or 50. It needs to have a bounded time delay. But a lot of this technology already exists. The big data community has a need for large bulk data transfers. There are RDMA, remote direct memory access techniques. But often in a cloud, this is kind of a black box. So I will send a message, and it will magically appear on the other side that data structure. Oh, it's very disconcerting watching yourself with a delay. So I'm going to just, hopefully it doesn't turn off. Hopefully. Yes, so the Amazon Scalable Reliable Datagram is such an example of this technology. So it's originally designed for some kind of big data things. If you're doing, I don't know, fluid dynamics or something where you have large amounts of data you need to get between instances. And this is the internal Amazon protocol that's used in CDI. So CDI is probably the obvious thing. We go, well, we have CDI. Well, yes, it handles a lot of the challenges that we discuss. It's an array of exchanging data between Amazon cloud instances, in particular pixel data structures, metadata, and other things. And Amazon guarantee throughput reliability, and they have a latency bound. So they have a paper where they show, I think they do it in terms of US frame rate, so 33 milliseconds, and they show this protocol will always deliver the data on time or better. And this really is a big step forward for the industry. But there are parts that need input from the GCCG working group. In particular, this timing model doesn't really have a full timing model that we'll talk about, well, in John's section, or the section I'll talk about that was John's section, we'll talk about in quite a bit of detail. So in the end, what GCCG will do is leverage CGI for applications where available, so in Amazon, but other cloud providers will be free to define their own protocols underneath, and it will just be that missing cloud-specific piece. So yes, what is the VSF GCCG working group? It is addressing this set of problems. In my personal opinion, this is maybe the last complex problem in broadcast production. There's last difficult problems. We now do live production over IP. It's pretty common in some facilities. But really the problem we're trying to solve is, how do I do a complex multi-channel production in the cloud, but have some kind of comparable latency to on-premises, and get it to the viewer via some traditional chains. And there are really a swathe of the technical challenges. So that's the link to what the working group is doing. Orchestration and control. For me, the boring and important part, but for many people in the room, the most exciting and interesting part. So each to their own on ground and cloud. So how do these cloud instances, for example, expose the maximum capabilities? What's the maximum resolution an instance can give out? Frame rate, etc. Is there some kind of orchestration layer that connects all the pieces together? What happens if resolutions and frame rates change during the production? Numbers of audio channels change during a production. You move from a film to an ad break, for example. Connection status. How does an instance or an instance say, I'm ready to have video go through me? And how do we control ground to cloud and vice versa elements? So this goes to John's section. So in the group, we looked at various different operating points, and we picked 3 in the end. So we started really at the high end, uncompressed, 2022-6, so SDI over IP, already defined. You could do this today. It may not be the best thing to do, but you could do it. Premium compressed, so JPEG XS at 200 megabits, and with some kind of dual path, probably reliability model. So probably the minimal latency. Looked at other means in between that, so latency bitrate quality trade-offs. So JPEG 2000 ultra low latency with stripes, JPEG 2000 full frames, AVC intra, and then interactive latency. So H.264 HEVC with a restricted VBV. So this would use something like some kind of retransmissions or dual paths or FECs, and it'd probably be off the order 20 megabits. 422 10-bit. So the stuff at the top, broadly speaking, you'd need a direct connect or whatever. I forget what the other cloud providers call a direct connect. Is it Highway? I can't remember. But there's their equivalents. Or you broadly would need some kind of telco assistance. Whereas the bottom 2, you could probably do using existing internet technologies. And then there was sort of a rate optimized, longer latency at a higher rate. So 3 to 10 megabits more delay. Again, similar sort of model, but 420 8-bit. And then since this was done during the pandemic, we thought just for completion, because lots of broadcasting was done over Zoom GoToMeeting at the time, and it was just sort of there, and it was decided that those 3 would be the ones that were chosen. So these 2 would be some kind of bandwidth optimized mode. Sorry, this one would be the bandwidth optimized mode. The one in the middle, some kind of interactive latency where you have a small GOP structure or progressive refresh, a small VBV. So this is sort of, both of these are widely used today over public internets and private networks, and some kind of premium compressed mode. And these are the standards, which I can talk about later, that are proposed. I think some of them proposed, some of them exist now to do all these things. So 2 areas in which we need to work on. I'm not going to be able to show it, but cloud to ground and ground to cloud, and also how do we exchange between these different applications. So this means that different like in a physical facility, you could plug in different vendors, and each vendor could do their own different thing in a particular different way. And with separated audio and video flows. And what you'd have out is something that you could even reconcile to the ground if you wanted to. It's quite a complex problem. So let's see how we solve this. Yes, so what we did was document premium. What we did is document the premium compress case, JPEG XS over TS. They have some NMOS style controls. So NMOS is the control plane used, a REST API, complex REST API used in 2110. The existing H.264, H.265 case been used for decades. It's widely used already. Probably not that much to be done. But the big complicated one, I think, is the time flow, time transport, time tagging model. Because as I mentioned, each instance has some kind of variable but bounded delay. And from me at the end, I'm generally the thing at the end in most facilities. I'm the encoder, I'm sending it somewhere. And I need to be the one that reconciles everything such that when I start pushing out video frames, I have buffered enough that I won't run out. And this sounds simple, but it's quite complicated. For example, if my video delay is 1 second and my audio delay is, say, half a second, I need to be able to adjust everything to hit the right timestamps such that when I start pushing video frames out, I can continue, because I need to be able to linearize this. I need to be able to linearize a non-linear model. So things may come in linearly from a ground. They end up being processed in a non-linear fashion, but I need to know the worst case of that non-linear processing such that when I start, I will always be able to push frames out. So yes, how do we treat time in concatenated virtual systems? How do we manage real time on the ground versus floating time in the cloud? The decision was quite profound. It sounds simple, but it's kind of profound in the sense that we want to, where possible, match time on the ground. So sort of a free running or time matching situation. But this means defining a whole new set of vocabulary that doesn't really exist. There's lots of other things that I'll show in a minute: catching up, managing drift, changes in frame rate, and reintegration to the ground. So in principle, for example, you could have, I want to have this portion of my workflow. Let's say this is quite a good one because it doesn't need to be necessarily frame accurate, but it needs to be reasonably close. I could say I have this as a fixed something in my facility. I will deport that to the cloud. It will take maybe a little bit longer, maybe 500 milliseconds more than it does on the ground, but that's probably okay, like for graphics. As long as it's not, as long as you don't see many of you probably watched the England game, as long as the little score counter doesn't take 10, 20 seconds to change, it's okay if it takes half a second. No one will probably notice. Too busy cheering or not cheering to notice, but that's fine. And then be able to have that reconciled, frame accurate if possible, with the ground. You've got different applications. They all need a way to exchange pixel formats and data. There's more and more metadata these days. So broadly speaking, we're going to use the AWS CDI structures. We still have to be able to accumulate latency across different applications. And where I mean accumulate latency, actually I now mean the worst case latency. And see how that's communicated between applications or between instances. So yeah, the whole point is to have some kind of time variability. We don't want to just recreate this lockstep pattern that we've had on the ground for decades. So we can have some kind of variability, so applications can run slightly faster or slightly slower than they may do in an ideal world. The cloud is a shared resource, so there are certain processes, for example, that you can run certain instructions on, and you'll lose 20% of your throughput straight away because they'll immediately go into power saving. That's kind of a good example of where you may not be able to predict this. And some processes at the end, probably the encoder is the biggest, most important one, but there might be others I haven't thought of, need to take a bunch of variable inputs. So video that has a variable delay, audio that has some kind of variable delay, subtitling, other types of metadata that has some kind of variable delay, but produce a linearized output for the ground. Not sure if I mentioned, but the reason you're able to do this on the web today with cloud production is the web linearized outputs. You can burst all you want, but because they've picked a number to buffer that's large enough that they've estimated as the worst case, that's fine. But the target goal is to have something comparable to the ground. So you need to go and measure all these things and understand how they accumulate. So in the end, the input buffering of the thing at the end needs to start buffering, but once it's started, that's it. So what are the sources of this variability? Network induced, we've at least decided, and different cloud vendors may change this, but we've assumed that's kind of relatively small, that implementations may vary, and that may actually end up being measurably large, but we've assumed it's a bit like the ground. It's small compared to the overall delay of the process. And then processing steps. So various different processing steps may have an average, but a bounded higher latency. And the vocabulary is challenging because this is completely different vocabulary that we have to kind of make up and people understand. So TX variability, how early or late the signal can be. There's some kind of variance, some kind of planning for the worst case. An actual delay is basically the planned delay plus some kind of real-world variability. And this is where it gets a bit. So we're pushing frames of chunks. So these could be frames, fields, stripes. So stripes would let us get to some kind of subframe processing, which isn't normally done in software. We do a little bit in our company, but the vast majority of software video processing is frame-based. So we define this value called Lmin, which is the soonest amount of time from input to output. You can work out, I have an input time where the buffer came to me, an output time, and there's some egress transit. Lmin is the important one, which is the worst case at the 99th percentile. And 99th is used for simplicity, but we can argue all day whether it's 99.999 or 99.9999, but We have to draw a line somewhere, but that part of the bell curve is relatively impractical anyway, but we pick a number. But then what happens if there's a glitch on the input, or for some reason one of the processes runs too slow, it finds an edge case. This does happen in the real world. Some of my colleagues in the room know. We have clips in our office that somehow, for various reasons, pick the worst case of processing delays. They happen to have movement that cause absurd CPU loads beyond what we're normally used to. This can happen. These are not deterministic processes these days. There is an area of variability to it. So what happens if something is late, for example? So I don't know. You have a frame rate converter, and you found a sequence in the frame rate converter that causes it to use a ton of CPU and take twice as long as it should. What should downstream steps do in that case? Does it need to maintain cadence? What we do normally is, duplicate frames, try and hide the audio clicks, this sort of things. But we need to kind of define this. But I guess the big outcome of all of this, the one thing is, variability on the input accumulates onto the output. So I see lots of presentations about how we're going to do cloud production, and this is the bit that people hand wave away, where they haven't really thought about, I need to deliver to a linear chain. When you're delivering to the web, fine, you can burst up and down all you want. You've got plenty of bandwidth. You don't have to, if your frame's late, just burst it at 100 megabits. No one notices. This is what happens today. But when you're delivering to a linear chain, you're delivering to satellite, terrestrial, where you have a fixed amount of bandwidth. You can't just burst when you're late. So many of the sort of presentations I see about this topic sort of treat the world like an animated GIF. I'm just going to push frames along. But anyone who's implemented an encoder or a decoder knows that some frames are bigger than others, so some arrive earlier. But you have to be aware of when they're actually meant to be displayed or meant to be decoded, not when they actually arrive on the wire, which are two different things. But when you accumulate all these different processes that have different delays, you need to actually say, the worst case will be 1 second, and anything beyond 1 second, I have to try and conceal it, for example. So yeah, consensus views. A lot of new lingo that needs to come up. So this is all very hand-wavy because many of the words haven't even been defined yet. Inter-instance, so intra-cloud, which is very, very not confusing, in a virtual facility. So consensus views, we're going to rightly or wrongly use NMOS. We're going to initiate connections. What kind of language are we going to use in this thing? A very open topic, certainly, in the working group. What are the transport parameters? How are we going to put this in writing? Honestly, is the biggest challenge of them all. Because if you make it too complicated, no one's going to bother. They'll just make it up as they go along, and like they'll do on the web. They'll just make a number. They'll pick the delay to be 10 seconds, and that's big enough always. But then, what's the point when you're doing live production? You'll see a goal twice. You'll see a car overtake itself twice when you cut between cameras. Like, you can't just pick a number. You've got to do this. But as with many specs, if you make this too complicated, no one's going to understand. Buffer handoffs in the cloud. Unfortunately, the best defined one, the one that everyone knows how to do, is probably the worst one to choose, which is the 2110 packing format. And if anyone's looked at that, that's the most software unfriendly format of them all. However, everyone knows how to process the most software unfriendly format. There are other proposals, one of which is mine, which is the Cloud Exchange format. It's on GitHub, where, for those who are interested, we pack 8 bits together and then stick the 2 bits, the lower 2 bits at the end of the line in the sort of blanking interval, which means that many applications that only need to process 8 bits of data, like multi-viewers, can just work on that data straight away. And if an application needs to process 10 bits of data, they'll have to unpack anyway. So it gives a net advantage because they'll have to unpack the 2110 packing anyway. So if the packing can be such that 8-bit applications can process the data already, that's a benefit. Audio formats, we need to just decide something. I think the 2110 one is a bit legacy now. I think it's Big Endian. Big Endian is lost. Timing and transport. Also transport, like audio. We don't want to be doing crazy RDMA buffers for 2 megabits of audio, like spinning up these expensive instances to transport 2 megabits of audio via 100 gigabit high performance paths. Overkill. Metadata subtitling, same problem. Probably will end up being a TCP socket. Low bit rate, it's good enough. Inter-envelope arm's length handoff between clouds, so that's, yeah.
So you're saying that you have to spin up big instances, not because you need the power, but because you need like the fabric adapters on
Yes.
posh instances.
Yes. At the moment, yes. In the CDI case, you have to have their, is it scalable elastic fabric adapter, I believe, which restricts you to certain instances. But if you're just an audio processing gateway, you don't need to spin up one of these to do your 2 megabits of audio. I mean, this is a solved problem. Like, do your simple audio processing on something more reasonable. Into envelope. So I think this is between availability zones where you may not get such a such sort of RDMA style. I will drop off a buffer and it will appear on that side, or between cloud providers, which is a similar case to ground to cloud. So where do we go from here? Jargon heavy, unfortunately. I'm really not a big fan of jargon, but the ground to cloud working group is producing a work in progress document to document and forward to the Advanced Media Workflow Associations. The Advanced Media Workflow Association is extending the network media open standards to other stream types. The Video Services Forum has already published Technical Recommendation 8, which is JPEG XS, I think. And then TR09 is the control of the JPEG XS style. There'll need to be more work in NMOS to handle transport streams. NMOS was not designed for transport streams. NMOS was designed for 2110. The question is, do we actually really need this? Because we've been using transport streams over IP for 20 years. But there's never really been a control plane, and some people, rightly or wrongly, actually have no strong opinion for once. For once, on whether we need a control plane for transport streams. There are, that was an IBC. There are other talks, I think on TR08 and TR09 on the IP showcase, and there are other things going on in the VSF and AMWA to help this work move forward. Any questions? I don't know how much time we have, but certainly latency accumulation is one thing I spend a lot of my time explaining, and so if there are questions, please ask.
No, that sounds very cloudy.
It's all in the cloud?
Sorry, yeah, but it doesn't feel very cloudy. It doesn't feel cloud native in any way. Sorry.
I'll come back to you. Because just for the video, that's all. Sorry.
So I'm kind of unclear. That was really great, thanks. I was really clear on a lot of that. But what I didn't quite understand is, when you're talking about accumulating this variable delay,
yep.
Are you talking about modeling it and predicting it, or are you talking about measuring it in real time?
No, I'm saying each instance will know, based off their particular product, what their average delay is, and their actual worst case. So I don't know, let's look at my product. I know it will take me 20 milliseconds to decode a frame normally when I have all the CPU available, etc., etc. But I might have, in the worst case, I might have someone else on that instance using instructions that cause a power save drop, like cause an energy saving mode, so they cut my CPU by 20%. You can do that with one instruction on certain CPUs, for example. Or I could have a clip that's got like the worst case of movement and colors and this and that. And I know that will take 39.5 seconds, and I know that from a software perspective in the L99.99 case. And what an instance has to do is advertise that worst case. Because in reality, during that process, that will be a very variable thing based off the content, based off CPU capabilities at the time. Because CPUs these days are not static. They move. If you check on Linux, they move up and down all the time based off power saving, and all these things are on by default these days, even in the cloud. So if me and you share a cloud instance of a particular Intel CPU, and I run this particular instruction, both of our processing power goes down by 20% because we're on the same CPU. So this is something that the latency accumulation needs to think about, both application specific and host specific, and probably other factors I haven't talked about.
So you've got a modeled maximum latency
based off everybody's
declarations.
Everybody's declarations of their worst case.
And then in reality, you're tracking timestamps on individual frames or something like that to see what the real...
We can talk about, there's probably not enough time to talk about that,
okay.
But yes.
I'm just trying to kind of understand the technical area of development.
Probably not enough time to talk about that, but yes.
All right, thanks.
Sorry, did you want to ask something?
Yes. It feels very traditional in its approach, and I appreciate
non-linear processing. Why does that happen on the ground?
Everything in there seems to be tying us back to a very synchronized approach.
It needs to be synchronized to the ground. Otherwise, spin up OBS and vMix in the cloud and have fun. Yeah. Send your YouTube streams. Make it 30 seconds delay. Have fun. But this is not a professional broadcast. When you're 30 seconds out, who cares? Have fun. When you have no timing model,
the
have fun.
object-based paradigm that many people are trying to use, it doesn't feel like we're going that way. We're still trying to retain all the broadcasting stuff that we have and carry it.
We're on the ground. We're on the ground. We need to put ads in. We need to put ads into linear channels. We need to have, when we cut between cameras, we can't have, oh, but this camera is a different model and has a different thing, and we've just made up the numbers based off this one's a Logitech and this one is a different one, and oh, I see a goal, and then you cut, and the goal comes again because the latencies are delayed. Like, this is cloud production. Like, when you produce something, a viewer expects a certain thing. I've spent a lot of time, for example, in racing cars, and it's really noticeable when you cut between the onboard versus the outboard, because if you look carefully, you can see the delays, and you can see that overtake happen again, but the operator does it in such a way that when they do the fade, they do it in such a way that they can kind of hide the delay. And there's lots of things that in the world to do that already. And if you're saying, oh, we're just going to do this in a web way where we just, and we just, make it up, like, this is not a high-end television experience. This is not what people pay good money for. This is OBS on YouTube.
Just one more question, and I think then we'll have to move on. So, Tim, was it?
It's kind of a continuation. The last one is when you've got decisions going back up the chain with it. I think it's fine if you've got an OB truck where you've got edits on that location, but if you're making cut decisions or re-racking cameras and you've got a stacking effect, if you say to back through comms, oh, cut to this, and there's a big stacking effect on that, they're going to cut to something that could be something else. I know, like, we talk about racing cars, like, with Formula 1 they have push to air, don't they? Where some, cameraman can go, I need to push this to air because it's happening right now. It's faster than you can do in the vision mix thing. Is that the kind of latency place we're talking about here?
I'm just more taking, we have two sources. I have let's say an onboard camera is a good example, because this is a problem that happens today. Is I have an external circuit camera and I have an onboard camera. And because that onboard camera is doing RF or 5G, that's already got an inherent delay. And so you have to be really careful when you cut between the two, so the viewer doesn't see, let's say you cut to the external shot and then you cut to the internal shot. So they see the overtake, you cut internally and they see the overtake again. Well, you have the same problem here because you have all these sources on the ground, and if you don't time them correctly on the, or if one of these steps is a mixer, if you don't have a rigid timing model before you hit a mixer or you hit the encoder that's coming out, you're going to cut between this guy that's got 1 second of delay and this other guy that's got half a second of delay, and you're going to see a goal or an overtake again. And so if you haven't reconciled your timing model through all the steps of that process, and there may be all sorts of things that we haven't even dreamt of yet, but it doesn't matter as long as they declare their worst case. And said applications could also work in terms of chunks to minimize that, but it doesn't matter as long as it's declared. Those two will be in time at the point they need to be in time, but every other point they don't need to be timed. They can be going, camera A can be processed faster than camera B, but as long as it's reconciled somewhere. And that's the cloud element of it, is things can be going faster than others. On that instance, there can be someone pushing it into power saving mode, whereas that one there isn't. So that guy will go faster than that guy. But it doesn't matter, because as long as the guy at the end, or here, reconciles all of this. That's really the bit that I've seen missing in all of the talks. I've seen this bit hand-waved away. It's one of the things when you build an encoder or a transcoder. Certainly a transcoder is doing all of this. A transcoder is taking a variable input, a TS, linearizing it, and then delinearizing it, but then sending it over a linear channel again. And it's a much more complex version of a transcoder because it's doing it in the uncompressed domain and using a vendor-specific cloud protocol.
Thank you very much to Kieran. Yeah, absolutely.